More than 8 billion tons of plastic waste currently saturate the global ocean waters, forming immense drifting accumulation zones. United States engineers responded to this logistical challenge by designing an intelligent collection architecture. Instead of chasing individual debris fields, the system functions as a stationary interceptor. But this is just the beginning. Why does the mechanism rely strictly on natural ocean currents? Active pursuit of trash with fuel-powered ships would create a massive energy deficit. The design instead harnesses the water's own kinetic movement to guide waste directly into the capture zone. At first glance, the structure appears to be a simple passive floating pipe, but in reality, it is a calculated hydrodynamic trap. One can notice how the U-shaped barrier funnels floating plastic toward a central retention point while allowing aquatic life to pass safely underneath. The equipment gradually concentrates the debris for eventual extraction. It gets more complex further on. The system maintains stability even amidst the unpredictable variables of the open sea. 20 million tons of debris flow into the ocean every single year, creating a shifting landscape of waste. Nearly 80% of this mass is plastic, a material so resilient that it endures underwater for centuries without degrading. These fragments accumulate into enormous floating garbage zones that drift across the open water. One can notice how the debris forms dense layers on the surface, trapping everything in its path. But this is just the beginning. Why is this material dangerous enough to alter the entire marine food web? The fragments do not merely float passively in the currents. They quietly seep into the ecosystem, disrupting the balance. This eventually harms more than 700 ocean species and impacts humans at the top of the chain. At first glance, this accumulation looks like useless refuse, but in reality, it represents a significant reserve of raw materials. If properly retrieved, a large portion transforms into repurposed plastics and engineered fibers for the textile sector. Reclaimed metals are also separated during the process. Transition to the next level. This recovery process saves thousands of kilowatt hours of energy compared to primary production. Consequently, the method prevents millions of tons of carbon dioxide emissions from entering the atmosphere. This helps shape a circular ocean economy where discarded materials are given a new life. The waste effectively finds a new purpose beyond the water. 5 to 10 tons of mixed marine waste are gathered in a single cleanup operation lasting 8 to 10 hours. Why deploy highly specialized technological systems in major accumulation areas like the North Pacific Gyre or the Gulf of Thailand? Gathering such vast volumes of debris in the unforgiving conditions of open waters requires industrial precision to handle the load. Dedicated cleanup vessels serve as the primary workhorses in these zones. Each vessel operates with 2 hydraulic mechanical arms that extend outward, sweeping across the water in a broad, fan-like pattern. One can notice how these arms guide drifting refuse, from plastic bottles and discarded bags to derelict fishing nets, into floating channel systems linked to the ship. Stainless steel conveyors positioned on the deck receive the material, funneling it into large holding compartments. But this is just the beginning of the reclamation journey. Not all discarded material makes its way into the open sea. A large share becomes lodged in rivers, reservoirs, and canals, where it builds up into dense layers that restrict water movement. Clamshell excavators mounted on dump trucks are deployed in these environments to combat the blockage. Each steel bucket, weighing close to 1,000 pounds, descends to reach deep below the surface and scoop up mixed debris, bottles, plastic bags, branches, and even old tires. Every single lift removes between 500 and 1,000 pounds of trash with a mechanical crunch. With the help of hydraulic power, one crew can clear a river segment hundreds of feet long within just a few hours, nearly 10 times faster than manual cleanup. However, the process is only gaining momentum. In many coastal regions, collection still depends on local fishermen and volunteers who use small nets and hooks from their boats under the scorching sun. At first glance, their contribution seems minor compared to heavy machinery, but in reality, this effort represents the essential first step in the ocean's recycling chain. Each individual may retrieve only a few hundred pounds of waste per day. Trash skimmer vessels carry the collected waste back to shore after the retrieval stage is finished. These specialized boats, measuring roughly 25 to 30 feet in length, are engineered solely for capturing floating debris. A compact skimmer can accumulate around 5 tons of material during an 8-hour operation. When its storage area reaches capacity, a hydraulic conveyor at the bow lifts and discharges the entire load into the receiving zone on land. And this is not the limit. The preliminary sorting phase officially starts immediately upon offloading. The freshly offloaded mixture includes a wide spectrum of items: plastics, metals, wood, seaweed, and organic sludge. Conductors conduct a rapid inspection to remove oversized or dangerous objects, such as steel nets, oil buoys, and tires. The remaining material is then shoveled onto a feed conveyor that transports it into the screening system. Transition to the next level. It is visible how the trommel drum classifies the waste by particle size inside the sorting line. Sand, silt, shells, and tiny fragments pass through the perforations, while bottles and packaging stay inside. The residual stream, which consists mainly of plastics and nylon, moves to a manual sorting belt where workers separate each category. Thus, the recovered materials are prepared for a new life and purpose. 7 major plastic types circulate globally, but the path to renewal begins with a single critical step of separation. Why is the washing stage so aggressively thorough for marine debris compared to standard household waste? It would seem that simple sorting would suffice to prepare the material for grinding. However, plastic retrieved from the ocean has often spent months or years submerged in salt water, becoming heavily coated with stubborn algae, oils, and microbial growth. Therefore, before any true recycling occurs, the material must be stripped of these contaminants. But this is just the beginning of the purification process. Inside the processing zone, the material enters a mechanical wash tank, where rotating shafts equipped with paddles churn the water ceaselessly. One can notice how the turbulent flow scrapes off surface buildup while rinsing away loose impurities. The liquid is formulated with gentle cleaning agents and a chloride neutralizing compound to chemically eliminate salt and oil residues. In some facilities, engineers maintain the water temperature between 160 and 180 degrees Fahrenheit to boost the effectiveness of sterilization. The cleaning phase typically lasts from 15 to 30 minutes, depending on how heavily the waste is polluted. Once cleaned, the materials move into a drum washer, which spins while blasting them with high-pressure water streams to dislodge stubborn sand. Afterward, a float sink tank classifies the plastics by density. It gets more complex further on. Polyethylene terephthalate settles at the bottom, while high-density polyethylene and polypropylene remain afloat like corks. The freshly washed material is then transferred to a centrifugal dryer to extract remaining moisture, followed by hot air drying at roughly 170 degrees Fahrenheit. In larger plants, ozone-based deodorizing systems are added to treat vapor emissions. This removes organic smells and neutralizes bacteria before the next phase. At first glance, the pre-sorting stage looks like a simple repetition of the initial intake, but in reality, it is a precision operation dividing plastics by category and size. The mixed plastic feed moves into a large rotating steel drum where the material tumbles continuously. As it turns, small perforations let dust, sand, and fine particles drop out. Larger bottles continue moving forward, ensuring that course-sized classification prevents blockages in subsequent equipment. And this is not the limit. Next, the stream travels along a manual sorting line where workers rapidly pull out unwanted items such as metal cans, nylon, and cardboard. Simultaneously, an automated cap and label remover uses vortex air pressure to strip away different plastic components. Magnetic detectors continuously scan the flow, ejecting any residual metal pieces or staples. After this mechanical purification step, the remaining material consists primarily of clean, uniform bottles ready for the grinding phase. The bodies of the plastic bottles are directed into a high-speed granulator chamber. Inside, hundreds of alloy blades spin at several thousand revolutions per minute, slicing the bottles into small pieces known as flakes. In a single hour, one machine can handle between 2,000 and 3,000 pounds of plastic. One can notice how the equipment transforms what was once a mountain of bottles into a steady flow of uniform material. The process is only gaining momentum. This grinding step not only reduces the material's bulk, but also enhances energy efficiency in later stages. Once the plastic is broken down into fragments, it melts more quickly inside the extrusion unit, cutting electricity use by up to 40% compared with melting solid plastic chunks. The resulting flakes are only a few inches in size. This ensures they are small enough to move through the next thermal processing systems without causing blockages. At the microscopic scale, optical systems take control with high-speed sensors examining each individual flake. The sensors assess color, clarity, and surface characteristics in just a few thousandths of a second. When the equipment detects a transparent fragment versus a green piece or an unrelated material such as wood, a precisely aimed jet of compressed air removes it from the mainstream. Transition to the next level. It is visible how each air pulse hits only one tiny fragment, weighing less than 1,000th of an ounce, without disrupting the nearby material. A single unit is capable of handling more than 1,000 particles every second, maintaining an accuracy level exceeding 95%. The outcome is a flow of clean, uniform plastic flakes sorted neatly into distinct categories. This forms the essential base for the pelletizing stage that comes next. The approved plastic flakes are delivered into a large-scale extrusion unit where they are heated to roughly 520 degrees Fahrenheit. At this temperature, the plastic liquefies and moves forward along a massive rotating screw. As the pressure builds, the molten material is forced through an ultrafine metal screen that captures any lingering contaminants. The refined plastic melt is then directed into an underwater pelletizing system. Everything only gets more complicated. Blades instantly chop the stream into millions of tiny granules known as pellets, which solidify in a closed-loop cooling circuit. These pellets become industrial-grade feedstock, ready for use in producing packaging, synthetic fibers, or even molded into brand-new bottles. From these recycled pellets, the factory moves into the pre-formed molding phase. Here, a partially finished shape is created before it becomes a full bottle. The material is checked for consistency and then sent into an injection molding unit heated to roughly 480 degrees Fahrenheit. In this softened state, the plastic is injected into a steel mold, forming a thick-walled tube with a threaded opening designed to fit a cap. Each preform is engineered to endure both elevated temperatures and internal pressure. This ensures stability during handling and the reheating stage required for blow molding. But this is just the beginning. Its compact geometry makes storage and transportation highly efficient for delivery to bottling plants near consumer regions. The camera glides along the line where preforms reach a pliable, rubber-like condition before transferring into a stretch blow molding machine. High-pressure compressed air is injected through the neck. This causes the softened plastic to expand and press firmly against the interior surface of a metal mold shaped like the final bottle. A preform only 4 to 5 inches tall can stretch to nearly 4 or 5 times its original dimensions. Once the blow molding step is completed, each automated line produces thousands of bottles in mere seconds with an almost zero defect rate. Laser-based inspection systems constantly monitor wall thickness, symmetry, and transparency to maintain consistent quality. Beyond typical designs, the machinery can adjust volume and contours. It does not end at this stage. After leaving the mold, the bottle body is still extremely hot and prone to distortion, so it enters a rapid cooling chamber. The line uses either chilled air or circulating water for a stage that lasts only a few seconds, yet is sufficient to stabilize the structure. In some advanced facilities, the heat released from the freshly formed bottles is captured and reused to warm the cooling water. This greatly lowers overall energy usage. Before leaving the production facility, every plastic bottle must pass through rigorous quality checks. Optical sensors, high-resolution cameras, and pressure testing systems identify even the tiniest flaws, including micro cracks or trapped air bubbles. Certain samples are selected for mechanical evaluations such as tensile strength, compression, and impact resistance. For bottles designated for food applications, additional chemical screening ensures that no harmful residues are present. And this is not the limit. Only after satisfying all requirements are the bottles grouped together, stacked onto pallets, and shrink-wrapped for protection. Automated palletizing robots arrange thousands of units with inch-level accuracy, tagging each batch with a unique traceability identifier. From the central distribution area, the finished goods are shipped to beverage factories or supermarkets. Each newly produced bottle represents the outcome of a circular technological system where discarded material is reborn. The transformation cycle concludes here, delivering a valuable resource back to the economy. Thousands of purified granules emerge from the final extruder to complete the cycle. Why is this complex journey from the ocean to the factory floor so critical? At first glance, it looks like simple waste management. But in reality, every ton of this reclaimed polymer reduces the industrial demand for virgin petrochemicals. The transformation prevents pollution while supplying heavy industry. One can notice the uniformity of the final product as it fills large transport bags. Waste drifting across the sea has been captured and rigorously cleaned. The material is reborn as a valuable resource capable of powering modern manufacturing sectors. But this is just the beginning. Detailed sorting and washing have stripped away the history of contamination, leaving only pure polymer chains ready for molding. The process concludes this phase, opening the road to formation.